Hello everyone, my name is Richard Jonker. I'm from the University of Aveiro, more specifically IEETA, and I represent the Bioinformatics group. Today we'll be presenting our work at the MultiCardioNER challenge. So to give an overview of the challenge, we participated in the MultiCardioNER challenge, and the goal of the challenge is to perform better recognition of clinical variables in cardiology. More specifically, the challenge was focused around cardiovascular diseases and to identify the entities of cardiovascular diseases in clinical text. Every year, cardiovascular diseases are responsible for around 18 million deaths worldwide, according to the World Health Organization. So the MultiCardioNER challenge was split into two tracks. We participated only in the first track, and the first track was called CardioDis, and it's related to the adaptation of general clinical concepts, recognition systems to cardiology. So in general, the idea was we were given data trained on or data for general diseases, and we have to adapt this to the cardiology domain. The second track was multi-drug, which was the adaptation of the multilingual adaptation of cardiology entity recognition systems again. So our group has had a relatively strong history in entity recognition related tasks. So we have participated and achieved top results in several entity recognition tasks. So this started already in BioCreative 7 with the NLM Chem track, followed by BioASQ 11 with MultiCardioNER, BioCreative 8 with BioRed, which was a mixed entity recognition, entity linking, and relationship extraction task. And then finally, our newest work was BioCreative 8 with the symptoms challenge. After the symptoms challenge, we decided to propose a generic Multi-Head CRF model to tackle these types of tasks, since we were using more or less the same architecture for all of them. And we decided to build a bit on this architecture and propose something new. So what we ended up proposing was the Multi-Head CRF model, which is already published, and you can study it more there. But to contextualize the model for this presentation, the model was designed to be a plug-and-play entity recognition model. And the main importance of this model was it was able to handle overlapping multi-class entity recognition. And from what our experiments led is that it achieved competitive performance on several biomedical datasets, namely the symptoms, MedProcNER, DISTIMIS, and PharmacoNER. And it was able to do this at the same time. So the entity recognition was trained for all 4 datasets at the same time using one model. And the idea was to obtain a model with the same performance as a single class entity recognition model, but without training several classifiers. So we trained one single model for many entity recognition tasks. And the general architecture or the idea behind the architecture is to use a shared transformer with several classifier heads, which allowed us to enhance the computational efficiency and ensure scalability for multi-class NER tasks, whilst maintaining high performance. So this led us to our research questions, because we had our Multi-Head CRF model, but we never really tested it on true single-class NER models. So we wanted to see if our Multi-Head CRF model was still capable of delivering competitive out-of-the-box performance in this new task, the CardioNER dataset. And then our second research question was, how effectively can a model trained on general concepts adapt to the specialized domain of cardiology cases? So this is to see how well the domain adaptation actually works out. So our methodology was fairly straightforward, because we used our Multi-Head CRF model. The model was plug and play. We just have various hyperparameters that we can tune to optimize the model further. And our hyperparameters were mainly related to augmentation techniques. So the model features several augmentation techniques. We used the random token replacement augmentation technique, where you substitute random tokens with other tokens from the dictionary. And this came with 2 hyperparameters, namely the augmentation probability and the percentage tags. And these two control how often or how many documents or the probability of a document being selected and how much of the document is augmented. Further hyperparameters include the number of hidden layers in the classifier head. So this is just to increase the depth of the classifier head. And finally, the context size. So we utilize document splitting in the pre-processing technique, and the context size describes how much of the document gets added into each split. As a final note, we utilize a Roberto-based Spanish model trained on clinical texts, also for name entity recognition as our base transformer for this task. Describing now the data set. So the data set in this work is not really standard, so to speak. So the event organizers gave us the DETI data set to train on. So this contains 1,000 clinical cases in Spanish text, which were annotated with diseases. And this data was part of the SPACC corpus. And then further, the DETI data set was previously released. However, the event organizers also released the new data set, the CardioCCC data set. And the goal is to then actually perform cardiology inference using the disease data set. So the cardiology data set contains 508 cardiology case reports, which the event organizers split into a validation set, which they released to us, and then a hidden testing set. So the validations data set was just over half of the data set, 258 documents. And the event organizers explicitly stated that we were allowed to mix and match the data together to see as we see fit. The remaining 250 documents remained hidden, which were used to evaluate the models. And in general, the data set uses the same guidelines as dismissed for annotation. Moving on, we then performed some brief validation for our Multi-Head CRF model to do some hyperparameter tuning. And just some basic conclusions was that our model benefited from the use of augmentation with a specific configuration of percentage tag of 0.25 and augmentation probability of 0.75. And then our model was optimal with one hidden layer per head and a large context size of 64. We can also see several of the other top 5 models that we tested on with hyperparameter tuning. You can see that they were all relatively similar F1 score. During the competition, we were able to submit 5 runs, and we had 2 separate approaches to the submission. So the first idea was to include the entire validation set into our training data. So these models were not really evaluated before the contest submission, so we include as much data as possible into the training set. And the second approach was to only use the training data, this data set, and we did not include the cardiology data. So the goal of this is to evaluate how well or how much benefit the cardiology data has in the training data, and to see how well the models actually adapt to the cardiology domain. So more specifically, our first run was an ensemble of our top 5 validation models, which included the validation set. So these models had an F1 score ranging from 74.2 to 74.87. Our second run was an ensemble of the top 17 runs trained with validation sets. So these contained models with an F1 score of 74. The third set run was a model containing the best performing model without validation. The fourth run was an ensemble of all of our models without validation, and our final run was an ensemble with all of our models, including with a mix of both validation and no validation. So according to the official results, we achieved the top scoring system, which was the second run. And some brief conclusions we can make is that including validation did improve the performance by around 6 points on the F1 score. However, that being said, the base systems did handle cardiac data quite well. However, considering how small the data that we add, it is beneficial to add the data to the data set. We also note that large ensembles are better, and all scores were significantly above the median results. Finally, to describe our discussions and conclusions. So back to our first research question, which is how well does our models, how effectively can a model trained on general concepts adapt to specialized cardiology cases? So in general, the models adapt very well to the cardiology domain. However, if you have some data that you can use to train additionally, it significantly boosts the performance. And in general, our model was really good in this task, our multi-head CRF model. This is evident by the top performing systems and the consistency of our systems even without the training data, the additional training data. We can see that our performance in the competition was quite well. We also note that the hyperparameter tuning did not have a very big impact of the performance of the model, and the base model was very consistent. And the results that we obtained here just generally coincide with the conclusions we drew from the original paper. This indicates that the model is capable of performing well in single-class NER models as well as the multi-class NER, which was discussed earlier. So we'll now address any questions if you have any. Thank you.